Welcome to Learning Labs with Cornerstone. I'm Philip.
And I'm Erica. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
In this pair of activities, students will first discover how thermometers display temperatures in sunny versus shaded areas and why meteorologists always use shaded temperatures to tell us about the day's weather. After that, students will simulate and observe differences in satellites based on orbital position.
Here's what you will need for this experiment. 4 thermometers, or 2 pairs of 2 different thermometers, labeled with permanent marker, number 1 and number 2 for one pair, and 3 and 4 for the other. A pencil or pen, a sunny day in a shaded area. If it's not nice outside, you'll need a desk lamp. As you place the thermometers, make sure that they are always on the same type of surface.
When outside, gather the students in the shade and tell them that today they'll be learning about thermometers and measuring temperature. Walk them out into a sunny area.
Ask the students, what does it feel like in the sun? Does it feel different than when we were in the shade? How is it different?
Place all thermometers in the sun or under the lamp, but not too close. We only want the light, not the heat, to affect the temperature. Leave 2 to 3 minutes for them to adjust.
The sun gives us lots of energy. Have the students stand in an area about 3 feet by 3 feet. When the sun is directly overhead, this area receives over 1,000 watts of energy. That's enough to power a hairdryer or a toaster oven. Most of the energy that gets to the earth from the sun is visible light. Visible light is a type of radiation that we can see. The different colors we see are different wavelengths of visible light. The rest of the energy from the sun is mostly ultraviolet radiation. This is more powerful radiation with shorter wavelengths than visible light. God made our atmosphere to absorb most of it. If we get too much ultraviolet radiation, it can damage our skin, giving us sunburn.
When the ground absorbs the visible light and ultraviolet radiation, it converts it into lower energy infrared radiation. We often experience infrared as heat or cold and record temperatures, infrared radiation, with thermometers. Now that you've waited a little bit, record the temperatures from your thermometers in the sun column of Table 1.
Place all thermometers in the shade or away from a lamp. Leave 2 to 3 minutes for them to adjust.
So we now know that the sun gives us energy as visible and ultraviolet radiation. What happens when it comes and hits the ground, or the thermometers, or us?
Objects in direct sunlight get hit by energy provided by the sun. The object will absorb some of this energy, which increases the energy of the atoms of the object. The more energy the object absorbs, the higher its temperature becomes. The atoms in the object move around or wiggle faster with higher temperatures. Darker objects absorb more energy than lighter ones, because the light colors reflect some of the energy back towards the sun.
So, when the thermometer is in the sun, the energy from the sun is increasing the temperature of the red liquid. Now you're ready to record the temperature of your thermometers in the shade column of Table 1 in your lesson plans.
Show your students their observations on Table 1. Which temperatures were higher, those in the sun or those in the shade? Did all the thermometers display the same temperature in the sun? How about in the shade? Was one pair of thermometers higher or lower than the other pair each time? If so, why do you think they were different?
Calculate the average temperature recorded among the 4 thermometers in Table 2 in your lesson plans. For younger students, tutors can average the numbers. Older students can be asked to calculate the averages in their group. How much variation is there in the individual thermometers compared to the average? Do you think that taking lots of different measurements gets a better or worse answer for the temperature? Do you think that one set of thermometers was more accurate than the other? Why or why not?
A meteorologist is a scientist who studies weather. Television and radio stations have meteorologists to tell us what the weather is and what it will be for the next few days. When a meteorologist tells us the temperature, he uses temperature from a thermometer that is in the shade, not one that is in the sun.
Suppose a meteorologist had his or her thermometer out in the sun. What would happen to the temperature if a cloud came by? Suppose a meteorologist had their thermometer in the shade. What would happen if a cloud came by then? Here's what you'll need for experiment 2. 1 piece of rope or string, 9 to 10 feet long, 3 students, and an area big enough for a 20-foot diameter circle.
Have 2 students stand at each end of the rope, facing each other with the rope tight. One student will be the Earth and will turn slowly. The other student will be a satellite in geosynchronous orbit. This means that the satellite student will walk in a circle around the Earth student, keeping the rope tight, always looking at the face of the Earth student.
Geosynchronous is made up of 3 Greek roots. Geo, meaning earth, syn, means with, and chronos, means time.
A geosynchronous satellite keeps time with Earth. This means that the satellite always stays over the same point on Earth all of the time and matches the Earth's rotation.
To do this, geosynchronous satellites must be placed very far from Earth, 22,000 miles away, along the line of the equator. At this distance from Earth's center, the satellite moves at about 10,000 miles per hour. That's pretty fast, but it's just fast enough to stay over one place on Earth. Moving faster or slower, or being closer or further away, means the satellite would not stay in the same place above Earth.
Set up like Unit 1, but place a 3rd student along the rope, but only about 1 foot away from the Earth student. This student is in low Earth orbit. They won't hold on to the rope. Instead, as the Earth and geosynchronous student begin to move, have the low Earth student walk in a circle around Earth. But they will take 2 steps for every 1 step the geosynchronous student takes. As the low Earth student orbits Earth, they will need to duck under the rope.
Count how many times the low Earth student orbits Earth in the time it takes for 1 Earth rotation.
Low Earth orbiting satellites are placed 1,200 miles closer to Earth's surface. Some of these satellites and structures, like the International Space Station, are within 300 miles of Earth's surface. This is technically still inside Earth's atmosphere, though the atmosphere is far too thin to breathe, and when working outside, everyone still puts on spacesuits for protection. However, there's enough atmosphere even at these heights that can slow down the satellites a little bit by friction.
Because they are closer to Earth, the planet's gravitational pull on low Earth orbiting satellites is stronger than the pull of the satellites further out in space. To stay up without falling to Earth, these satellites must travel almost double the speed, 18,000 miles per hour, of the geosynchronous ones. Low Earth orbiting satellites will completely circle Earth every 90 to 120 minutes.
What are examples of geosynchronous and low Earth orbit satellites?
Because of their different locations, geosynchronous and low Earth orbit satellites have different tasks and uses. Here are 2 examples for each. Geosynchronous satellites include weather satellites like the Geostationary Operational Environmental Satellite, East and West, record the weather in the United States. Each covers about 2/3 of the country, so there is some overlap in the middle. DirecTV and Dish Network. People who use these satellites for television have small satellite dishes on their house pointing south. This is because the satellites orbit along the line of the equator and don't move their position over the Earth. Some low Earth orbiting satellites include the International Space Station, which was launched in 1998 as a joint effort of several countries. It can hold as many as 6 crew members and currently has 3, 1 US and 2 Russian. You can even see it at night, moving quickly across the sky. The Hubble Space Telescope takes pictures of space for NASA and has been in low Earth orbit since 1990. It has taken over 1.2 million observations.
That wraps up week 1. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Aaron.
And I'm Kira. In Learning Labs, we will take the Cornerstone Educational Supply Labs a step further and perform the experiment with tips and tricks for what to look for when performing your experiment.
Set of activities, students will learn about the behavior of light as it travels through materials. In the first activity, students will work with magnifying lenses and discover how images can be distorted. The students will then observe how images shift positions as they travel through different materials.
Here's what you'll need for our first experiment. A drawing compass with a pencil, 2 dual magnifiers and Cornerstone hand lenses, plain white paper for each pair of students, and pencils. Using the drawing compass, draw a circle on your paper. Draw a few other shapes as well, like a star or a square. Look at the lines you've drawn with the magnifying glass. Do the same thing with the hand lens. You might have to get a little closer to your face.
Here are some discussion topics for you to consider with your learners. Where in the lens is the image the clearest? Where in the lens is the image distorted? Can you see all the objects that you drew? What happens when you put the lens right on top of the paper? And what happens when you move the lens far above the paper?
How much bigger or smaller does the image look compared to the lens you were just using? Is the image distorted more or less? Can you see all of the objects that you drew with 1, 2, or all 3 lenses? How are the lenses shaped differently? Which magnifier made the image biggest or smallest?
As magnifier increases in power, it also increases distortion, especially around the edges. We have known this fact for thousands of years. Even Aristotle observed this. The ancient Greek mathematician and astronomer Ptolemy also noticed this and believed that it was the result of the Earth's atmosphere. Ptolemy was most famous for his long-standing model of the astronomical system that had Earth in the center and the sun, moon, planets, and stars orbiting around Earth. This was later disproved by the efforts of Copernicus, Galileo, Kepler, and Newton. However, the distortion effect of our atmosphere is too small to change the apparent size of the sun, moon, stars, or planets. When we look at the sun or the moon, when it is at or near the horizon, it appears larger, but this is just an optical illusion. Next, we will do experiment 2, bending light.
For this experiment, you will need the following items: a clear plastic cup, water, a straw or pencil, a 1/4 pound brick of clay, and a quarter.
Hand out a cup to each student and have them take the straw and place it in the cup.
Ask your students these questions. Can you see the straw clearly? Yes, because the cup is clear. Does the straw look like it is straight from top to bottom when you look through the cup? Yes, or perhaps a slight change. Take the straw out and fill the cup with water. Now have them put the straw in the cup again. Ask the students, can you see the straw clearly? Yes, because both the cup and the water are clear. Does the straw look like it is straight from top to bottom when you look through the cup? No. The straw looks like it is bent or broken somewhere. The part of the straw above the water does not line up with the part that is in the water.
You are now observing refraction. This happens because you are looking through air to see the cup, but there's water inside the cup with the straw in it. The water is clear, however, it is denser than the air. This causes the light to move through it at a different angle, so you can still see the straw, but it looks like it is shifted or broken. Now look down on the cup and see how the straw looks from above.
Ask the students to describe what they see. They should see that the straw doesn't look as long in the water as it does in the air. It looks short and or bent in a different direction depending on how they're looking at it.
Did you know that at sunrise and sunset we are seeing the sun when it's already below the horizon? It's true. Just like the refraction we saw with the straws, the atmosphere will refract the sun's light. Let's see how. Make a ball of clay about 1 inch in diameter and place the quarter into the center of it. Be sure the clay sticks to the bottom of the cup and have the student observe how the quarter looks in the cup and fill the cup with water.
Now have the student back up a few steps until they can see 2 images of the coin. One below through the side of the cup and one higher on the surface of the water.
Now you can see the coin in 2 places, one over the other. The lower image looks mostly the same as it did before the water was placed in it, but the upper image looks stretched out and flattened.
In our experiment, the surface of the water is like our horizon, and the coin is visible even though the real coin is below the horizon. This is what happens to our sun every day. The Earth's atmosphere bends or refracts the image of the sun so you can see it on the horizon, even when it would be below our line of sight if we had no atmosphere.
As students move forward or backwards, this image will disappear and reappear like the sun coming up at sunrise or sinking below the horizon at sunset. The flattened shape of the coin is similar to how the sun appears to look larger at sunrise or sunset. It's refraction.
That's week 2. Thanks for joining, and remember to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next time!
Welcome to Learning Labs with Cornerstone. I'm Ethan.
And I'm Julia. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and perform the experiment with tips and tricks for what to look for when performing your experiment.
Saturn is the 6th planet from the Sun and the 2nd largest planet after Jupiter. Saturn is so big that you could fit over 730 Earths inside it. Despite its size, it is mostly made of hydrogen and helium gas.
Saturn is most famous for its planetary rings. The rings are made mostly of ice and rock that orbit the planet, just like our moon orbits Earth.
You can sometimes see Saturn in the sky at night, but just looking with your eyes, you cannot see Saturn's rings. It was Galileo Galilei who first saw them using a telescope that he built himself. When he first observed Saturn with the telescope, he thought that Saturn was 3 planets, a big one in the middle and 2 smaller ones on the side. As he continued observing Saturn over time, Galileo got confused. The 2 side planets he was seeing seemed to disappear, with only the large middle planet, Saturn itself, still visible. We'll discuss why a little later.
Give out a copy of Illustration of Saturn's Rings to each pair or table of students. Have them observe the image.
Ask the students, which ring seems brightest? Which ring seems darkest? Why are some rings brighter than others?
Students will see that rings A and C are brighter than rings B and D. This is because there are more and/or bigger white spots in A and C than there are in B and D. The white spots in all of the rings can reflect or scatter light from the room back toward our eyes. The dark areas absorb the light.
Have one student in each pair or group hold their copy of Figure 1 in front of their chest. First, have these students stand just a few feet in front of their partner or group. Can you see that the rings are made up of lots of dots from this distance?
Now have the students holding Figure 1 move to the other side of the room, facing their partner or group. Can you still see the dots that make up the rings, or does the ring look solid?
Switch students so the other member of the pair can make these observations as well.
When we are close to the image, we can see the individual white dots easily, but as we move back, the rings look more solid and grayer. This is because the light that is scattered becomes blended together at bigger distances.
Because Saturn's rings are so far away, we cannot see the light from just one piece of ice or rock here on Earth. But Saturn's rings are made of millions and millions of pieces of ice and rock. Each of these pieces bounces a little light back to us. By adding all this light together, we can see Saturn's rings on Earth when using a telescope.
Show students the image of Saturn in Figure 2. Here is an actual picture of Saturn and its rings taken from NASA's Voyager space probe. Remember that Saturn's rings are made up of pieces of rock and ice that are anywhere from the size of dust to as big as your house. When the sun's light hits these pieces, some of the light is reflected or scattered back toward us.
Now show the class figure 3, pointing out that when Saturn's shadow falls on the rings, we can't see them. They are not reflecting any light. This image was taken from NASA's Cassini space probe.
Astronomers have discovered that Saturn's rings are actually very thin, but Saturn's dusty rings are only about 30 to 300 feet thick. That's as tall as a 2-story building or a 15-story building.
You can also see from figure 3 that Saturn has several rings with space in between them. The space in between is where there is very little ice and rock, so there is little to reflect sunlight. This creates the banded look of Saturn's rings.
So why are there spaces? These are created by very large blocks of rock and ice that can be as much as a few miles wide. As they orbit within the ring, they knock out smaller pieces. They sort of sweep up their orbit, clearing out all other particles. With nothing to reflect and scatter light in these areas, these big rocks create the dark spaces between the rings.
So how did Saturn's rings disappear when Galileo was looking at them? It happened because as Saturn orbits the Sun, we see the rings from different angles. Sometimes the rings are easy to see because they're at an angle that lets them reflect and scatter lots of light back toward Earth. At other times, the rings look thin because we are looking almost straight at them.
Show the students figure 4. What happened with Galileo is that he first saw Saturn's rings when they were at a high angle. The rocks and ice were reflecting lots of light, and he could see something in his telescope. Later on, the rings were at a very low angle, and they did not reflect as much light to Earth. They looked like they had disappeared, but they were still there.
Hold out a piece of paper in front of you, tipped at a slight angle. The students will be able to see the paper surface very easily.
Holding the paper at this angle, turn to your left a little bit. Students can still see the paper, but it appears shorter. Turn so that you are 90 degrees from the students with your right shoulder pointing at them. Ask them if it is easy to see the thin edge of the paper.
This is what happened for Galileo. As Earth and Saturn orbit the Sun at different speeds, our view of the rings changes so that it is sometimes easy to see and other times much harder to see.
Now we will perform an experiment to demonstrate how Saturn can be seen through its rings.
For this experiment, you will need a pair of scissors, a ruler, a white poster board or a piece of cardstock, glue, a black marker, a straight pen or a thumbtack, and a pencil.
Cut 3 strips from the poster board or cardstock that are each 1 by 6 inches.
Evenly space the strips so that their centers cross and glue the centers of the strips together.
Then use the marker to make 2 marks across the ends of each strip. Start the first mark 1/2 inch from the end of the strip and make the second mark 1 inch from the end.
Insert the pen through the center of the strips. Use the pen to enlarge the hole so that the paper blades easily spin. Then stick the end of the pen in a pencil eraser.
Spin the paper blades and observe how they look while spinning.
2 black rings are seen, but you can see through the spinning blades. This happens because your eyes blend the color on the paper strips as they spin, producing what appears to be solid rings. The rings around Saturn are made of chunks of ice and rock. Their movement makes them appear to be a continuous surface, as does the movement of the black marks on the spinning paper.
That wraps up week 3. Thanks for watching, and be sure to keep your Cornerstone lesson plans handy to help you with this week's experiment. See you next time.
Welcome to Learning Labs with Cornerstone. I'm George.
And I'm Kira. In Learning Labs, we will take the Cornerstone Educational Supply Labs a step further and perform the experiment with tips and tricks for what to look for when performing the experiment.
In this pair of activities, students will first explore the force of inertia and the effect of friction on a group of objects. They'll also discover that while all planets in our solar system orbit the Sun, each planet orbits at its own speed.
Here's what you'll need for our first experiment: a round cake pan, a marble, and a penny.
Have the students place the marble in the cake pan. Notice when left alone, the marble does not move.
This is an example of inertia. An object at rest will remain at rest. Only by applying enough force to an object can you get it to move.
Have the students roll the marble around the inside of the cake pan using a circular motion. When they do this, they have applied enough force to get the marble moving.
Roll the marble around and then stop moving the pan. Notice how the marble continues to roll. This is another example of inertia. An object that is moving will continue moving unless it is acted upon by a force.
Because very little of the marble's surface is touching the pan at one time, the marble moves around the pan easily. There is very little friction between the marble and the pan. Friction occurs when objects that are in contact with each other resist movement.
Now have the students repeat the activity using a penny. Have them compare the effort it takes to move the penny around the cake pan with the marble. They will also observe how long the penny continues to move compared with the marble when the pan is no longer in motion.
The penny takes a bit more force to get moving than the marble does, even though it weighs less. This is because the larger amount of flat surface the penny has keeps it in contact with more of the pan. The friction between the penny's surface and the pan is larger than the friction between the marble and the pan.
This is also why the penny slows down faster. More friction applies more force to the penny as it's moving. While the marble rolls smoothly, the penny is scraping along the pan, losing energy to friction and quickly coming to a stop.
This is experiment 2, running in circles. For this experiment, we will need 9-foot rope from week 1, space outside or in a large room.
All of the planets in the solar system orbit the Sun. That means that they travel around it. The orbit of a planet is almost the shape of a circle, but a little flattened, which we call an ellipse. It was pioneering astronomer Nicholas Copernicus who first proposed that the Earth and other planets orbited the Sun. Galileo Galilei confirmed this and also observed the first moons orbiting around another planet. Around the same time, Johannes Kepler discovered that the planets' orbits were ellipses rather than circles. In our activity, we'll discover why planets travel around the Sun. Lay the rope out on the ground as straight as the starting line. Have the students line up next to each other behind the rope. Have some students take steps on only the 1, others on the 1 and 3, and others on 1, 2, 3, and 4. The instructor will count out 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and the students will march a few rounds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2.
When we think about how our planet orbits the Sun, there are 2 things to remember: velocity and gravity. Velocity is the speed of a moving object in a particular direction. The students who stepped only on the 1 have the lowest velocity. They traveled the shortest distance during the marching time. Students who stepped for each number had the highest velocity and went the furthest in the same amount of time, while students who stepped out on the 1 and 3 had a medium velocity.
Gravity is a force that attracts objects. Bigger objects have a stronger gravitational force than smaller ones. Believe it or not, you have a gravitational force. However, it is really tiny. Earth is much bigger than a person, so when we jump, the Earth's gravity pulls us back down towards it. But we pull the Earth to us too.
Gravity is stronger when 2 objects are close to each other, and it quickly becomes weaker as the distance between the objects increases. So for us walking around on Earth, the gravity is strong enough to keep us on the surface. We can't move fast enough at the surface to escape Earth's gravity.
The Sun is much bigger than Earth, and its gravity affects our planet along with all the other planets, asteroids, meteors, comets, and other solar system objects. The sun pulls them closer to themselves. But the planets don't fall into the sun because they're moving fast enough sideways. They have enough velocity to keep their distance from the sun.
The closer an object is to the sun, the higher its velocity has to be to keep from falling into the sun. While an object further from the sun requires less velocity, because the sun's gravity isn't as strong. Now we'll do an activity to show how velocity and gravity work together to create a planet's orbit.
Pick up the rope and hold one end. Have 2 more students join you holding your end. The 3 of you are the sun. Have a 3rd student pick up the other end of the rope. The 3 of you who make up the sun should all be looking at the planet student. This student will face perpendicular to you. Make the rope tight between you.
Now have the planet student walk in a straight line forward. While they do, the 3 of you as the sun will pull the rope gently so that it stays tight, not letting the student walk straight ahead. By doing this, the planet student will move in a circle if the sun's gravitational pull matches the planet's velocity.
Pause for a moment. Tell the students to observe that velocity plus gravity makes an orbit. Also notice that the student at the end of the rope does not have to move fast to keep the rope straight, since the sun is only gently pulling the rope, showing a weak gravitational pull. Continue the demonstration for 1 full circular orbit.
If you have more students, have the first 3 sit down and have 2 more join you as the sun, and have another student for the planet. This time, student will take up the rope at its midpoint, not the end. Like before, the sun will pull the rope to show gravity, but this time, pull more strongly. Just remember this isn't tug of war. Make this a strong pull, but one that won't pull the student over. The planet must now try to walk in a straight path, but is pulled by stronger gravity. They should have to walk more quickly to keep going while the rope is straight.
Being closest to the sun, Mercury must travel very quickly to stay in orbit. If it moved slower, it would eventually be pulled into the sun. Venus moves a little slower because it is a little further from the sun. Earth moves slower still, and so on. Notice that as you go further from the sun, the planet's velocity decreases and the orbital time increases. It's all because of gravity and velocity.
That wraps up week 4. Thanks for joining us, and be sure to keep your Cornerstone Lessons plan handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Erica.
And I'm Nathaniel. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and perform the experiment with tips and tricks for what to look for during this week's experiment.
Students will model how our universe is expanding and discover how mass and gravity affect the orbits of planets and moons.
Here's what you will need for our first experiment: a balloon for each student and black markers. Our solar system includes 8 planets, asteroids, and comets all orbiting the sun. The sun is one of billions of stars in the Milky Way galaxy. Before the 1920s, we knew that we were in the Milky Way, but no other galaxies were known or even thought to exist.
This all changed when American astronomer Edwin Hubble made the first discovery of other galaxies far beyond our own. Using powerful telescopes, he was able to take pictures of galaxies that people thought were just somewhat fuzzy-looking stars.
Hubble wasn't finished, though. By observing these newly discovered galaxies, he discovered that the light coming from them wasn't quite right. It was like the light had been stretched out, making it look redder than it should. Astronomers call this stretched out light redshift. As Hubble looked from galaxy to galaxy, he saw this over and over again. But how does this happen?
Have you ever heard a siren from a fire truck or an ambulance coming towards you? The sound is loud and high-pitched. As it passes, the pitch drops and the sound lowers. This happens because the sound waves get bunched together as the vehicle moves towards you. The speed of sound plus the speed of the vehicle bunches the sound waves enough to raise the pitch. After it passes, the sound waves get stretched, and the speed of sound minus the speed of the vehicle stretches the waves a bit and causes the pitch to lower.
Light does the same sort of thing. When galaxies move away from us, the light waves get stretched because we take the speed of light
minus the speed of the galaxy. This shifts the light towards the red end of the spectrum. If a galaxy moves toward us, the light waves get bunched up a bit, shifting the light to the blue end of the spectrum. As Edwin Hubble looked from galaxy to galaxy, the light was redshifted, and it appears that galaxies are moving away from us and each other. That means that space itself is expanding and carrying the galaxy.
Allow each student to draw 15 to 20 dots, small stars, or other shapes on their balloon using a marker. Each of these will represent a galaxy within our balloon universe. Observe the distance between the dots and shapes. Now have the students blow up their balloons a little bit. Observe the distance between the dots and the shapes, noticing the shapes are a little further away from each other now that the balloon has been blown up a bit.
Now have the students blow up their balloons as much as they can. Observe the distance between the dots and shapes. Notice how the dots and shapes are now much further away from each other.
The dots and shapes on your balloon move away from each other over time because the balloon surface is expanding as it inflates. As space expands, it carries the matter inside of it, like galaxies, away from other areas. Galaxies get more and more distant from each other over time.
Edwin Hubble made two of the most important astronomical discoveries of the 20th century. He discovered that our Milky Way is only one of many galaxies in a gigantic universe. He also discovered evidence that the universe is expanding. Hubble created a classification method for galaxies, and one of our most important space telescopes bears his name, the Hubble Space Telescope. The Hubble telescope launched in April of 1990 and orbits 340 miles above Earth's surface. The Hubble Space Telescope is still taking images of our universe today. To date, it has made over 1.3 million observations.
This is experiment 2. All about orbits. For this experiment, we will need 2 pieces of heavy string or fishing line, 1 small weight, 1 medium weight, 2 large weights, and 2 spools. Before starting the experiment, tie 1 large weight to 1 piece of string. This will be at the bottom of your finished device. Thread the string through one of the spools. Tie the small weight to the other end of the string. This will be at the top of your device. Repeat these steps with the other large and medium weights.
In previous weeks, we've looked at how satellites orbit Earth, how Saturn's rings are made of rock and ice orbiting that planet, and how an orbiting body's velocity is related to the mass of the object it orbits. We've also looked at gravity and inertia. This week, we will bring these concepts together to look at orbits again, but we will change things up a bit. Instead of changing the distance from an object the body is orbiting, we'll look at what happens when satellites of different mass are orbiting objects of the same mass.
Hold the spool with the small and large weights, letting the large weight hang all the way down and the small weight resting on the top of the spool.
The weight on bottom represents a planet. It has a large mass. The weight at the top represents a satellite that orbits the planet. It has a mass smaller than the planet. The string between them represents the force of gravity that the larger planet exerts on the smaller satellite. You can see how the large planet is pulling down on the satellite.
If the satellite did not orbit, it would fall into the planet. If the satellite's velocity is too fast, it will escape the planet's gravity and fly off into space. To stay in orbit of a certain distance from the planet, the satellite must have a velocity that can match the pull of the planet's gravity. That velocity depends on 2 things: the mass of the satellite and the distance from the planet.
Begin spinning the spool with a small weight so that the small weight moves in an orbit around the spool. Vary the speed of your spinning so students can observe the orbit expand out and the large weight rise upward.
Ask your students, as the satellite moves further away from the spool, what happens to its velocity?
Now spin the spool with the medium weight. As before, vary the speed of your spinning so students can observe the orbit expand out and the lower weight rise upwards. The medium weight also slows down the further away it is from the spool.
Gravity is a force that attracts 2 objects. The bigger the objects and the closer they are to each other, the stronger the gravitational force is between them. However, the force of gravity decreases very quickly with distance. To overcome gravity, which is constantly pulling the satellite down, a close and low-orbit satellite must move very fast. The further away from the planet the satellite is, the slower it can travel because the gravitational force of the planet is much weaker. Do you remember this from week 1 when we looked at different types of satellites?
Have 2 students spin the spool sets at the same time. First, let them get the hang of it. Once they are comfortable, tell them to spin their weights so that the weight is only 1 to 2 inches away from their spool. Have the rest of the class observe both satellites.
Ask the students, which of the 2 satellites has the fastest velocity? Because the small weight has less mass than the medium weight, it has less inertia. With less inertia, it takes less force to move it. Gravity is a force, so the gravity of the planet pulls the small weight faster than the medium weight. To overcome this force, the small weight must orbit with a faster speed.
You can have students record the speed by counting the number of revolutions over time. Have 2 other students spin the weights, again with a short distance of 1 to 2 inches from the spool, using a cell phone or a stopwatch, and count the number of complete spins in 10 seconds. Multiply by 6 to get the revolutions per minute.
That wraps up week 5. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Thomas.
And I'm Kira. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further with tips and tricks for what to do when performing your experiments.
Activities, students will discover the conditions needed to make an eclipse, different types of eclipses, and observe why the total solar eclipses seen on Earth are both unique and scientifically important. Students will also compare the atmospheres of Earth and Venus.
Here's what you'll need for our first experiment. A desk lamp or large flashlight, and 2 or 3 of each of these. A quarter, a tennis ball or baseball, and a soccer ball.
Eclipses have brought awe and wonder to people throughout history, and for good reason. It is a very strange experience to see the moon block the sun in the middle of the day.
Did you know that eclipses happen on other planets as well? But the eclipses on Earth are quite special and scientifically very important. How does an eclipse happen, and what types of eclipses can occur?
To have an eclipse, you need 2 things: a source of light, that's our sun, and an eclipsing body, like our moon. When the eclipsing body passes in front of the source of the light, it will block some or all of the light in an area on the observer's planet.
Here on Earth, we can observe 2 types of eclipses, solar eclipses and lunar eclipses. In a solar eclipse, the moon passes between the sun and Earth, blocking the sun's light and making a giant shadow on Earth's surface. During a partial solar eclipse, the moon doesn't completely block the sun. This lets more sunlight down onto the eclipsed area on Earth, and the sky is not so dark.
During a total solar eclipse, the moon fully blocks the sun, and it becomes dark in the moon's shadow on Earth. Only during the period where the moon fully blocks the sun, called totality, can you look directly at the eclipse. Before or after this time, the sun's light is too strong and will damage your eyes.
Besides solar eclipses, we can also view lunar eclipses. These are more common and occur when Earth passes directly in front of the moon, blocking the sun from reaching the moon's surface. During a lunar eclipse, the moon's color changes to a dark, dusty red. This is because some light is scattered around Earth and dimly illuminates it. Place the desk lamp on a table and turn it on facing the students in class. Looking straight into the light would be like experiencing a day on Earth. Have the students stand approximately 10 feet from the lamp. Give each of them one of the objects, a quarter, a tennis ball or baseball, and a soccer ball, and have them hold it out in front of them.
Ask your students, how many of you can see part of the bulb from the lamp? How many of you can completely block out the lamp?
Have the students exchange objects with their neighbors so that each student tries this with each object. Now repeat the activity with students approximately 20 feet away from the lamp. What are the results this time?
Eclipses happen in other parts of our solar system as well. Planets like Jupiter and Saturn have many moons, so they too have eclipses on their planet surfaces.
But Earth's eclipses are special. Only on Earth is there a moon that just about perfectly fits over the sun to block it. Because of this near-perfect match in size, scientists on Earth are able to observe the gases that make up the sun's atmosphere. From these observations, the element helium was discovered, and scientists were able to begin understanding the composition of our sun and other stars in the galaxy. The famous physicist Albert Einstein had a major prediction of his theory of general relativity confirmed during a total solar eclipse in 1919. The eclipse showed that light was affected by gravity.
These discoveries would not be possible on any other planet in our solar system. With either no atmosphere, like Mercury, Mars, or thick, poisonous atmospheres, like Venus, too large or too small eclipsing bodies, like every planet with satellites or moons, and all other planets with extreme temperatures, the other planets are unable to either support life or have good conditions for scientific discovery.
Do you think that it's a coincidence that the only planet that has intelligent life is also the only planet where important scientific discoveries can be made? God knew exactly what He was doing when He created us and placed us here on Earth. It is a special planet indeed, created to be our home and a place for us to discover both of God and His wonderful universe.
Now we will do experiment 2. Atmospheres are a real gas.
For this experiment, you will need a desk lamp or a large flashlight, a piece of wax paper, and a piece of clear plastic wrap.
Earth and Venus are sometimes called twin or sister planets. That's because Earth and Venus are about the same size, have a similar gravitational force, and are made from rocky material with cores of iron. But after that, our similarities end. One big difference between these planets is their atmospheres. The atmosphere of Earth is made mostly of nitrogen gas and oxygen gas. These gases are clear and allow visible light to pass through the atmospheres and down to the ground. The ground then absorbs this energy and re-emits it as infrared radiation. Our atmosphere is able to keep in some of this energy through the greenhouse effect. Some of the less common gases like water vapor and carbon dioxide are able to absorb the infrared radiation and send it back to Earth's surface. So these gases trap some heat and Earth's temperature is overall mild. Importantly, Earth is warm enough to keep water as liquid in most places.
Venus's atmosphere is very different. It is made mostly of carbon dioxide and a little nitrogen gas. The carbon dioxide in Venus's atmosphere, the same gas that helps Earth trap heat, creates a huge greenhouse effect that traps most of the sun's light and heats up its surface so high that Venus is the hottest planet in the solar system, even hotter than Mercury. It is so hot on Venus that the metal lead would be liquid. And this atmosphere is so thick that the air pressure on Venus's surface is like being under 3,000 feet of water here on Earth.
Orange-yellow clouds of poisonous sulfuric acid prevent us from seeing any of Venus's surface using telescopes on Earth, but space probes and telescope observations have shown us that there's no way we could ever send astronauts to Venus. Even space probes, like the Russian Venera probes, didn't last long when the temperatures are nearly 900 degrees. Venera 13 holds the Venus survival record. It transmitted information and pictures for just over 2 hours before it broke under Venus's crushing atmosphere. Turn on the desk lamp. Hold a piece of plastic cling wrap about 6 inches from the front of the lamp.
Observe. The cling wrap is clear and allows most of the light to go right through it. This is like the atmosphere of Earth.
Next, take a piece of wax paper and hold it about 6 inches from the lamp.
Observe. How much light is getting through the paper? Is the image of the lamp clear, just a little distorted, or completely blocked? This is just like the atmosphere of Venus.
Try moving the paper forward to 12 inches, a few feet, or have the students hold it in front of them at their desks. Ask them to tell you how much of the lamp's light they can see through the wax paper.
That wraps up week 6. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson.
Welcome to Learning Labs with Cornerstone. I'm Brooke.
And I'm Phil. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
solar-powered images. Using sunprints, students will learn about photosensitive chemicals and solubility. Some steps in this activity are time-sensitive, so be ready to move quickly.
Here's what you'll need for this experiment. Super sunprints, 1 or 2 sheets per student. Extra acrylic sheets, a dishpan filled with water, pieces of cardboard, a variety of items such as leaves, flowers, small toys, buttons, or scissors, a timer, and some towels.
Sunprints is a brand of photosensitive paper. This means that the paper is coated with chemicals that will react when placed in sunlight. While strong, direct sunlight works best. The paper will react over time in any place where there is at least some light. It just takes longer when the light is dim or indirect.
So what chemicals are used in sunprints? Each sheet of paper is coated with a chemical known as Berlin green. That's easier to say than its scientific name, iron 3-hexacyanferrate. This chemical is made of iron, carbon, and nitrogen and is light green in color. Berlin green is water soluble, meaning that it will dissolve if placed in water. If you put the paper in water before exposing it to sunlight, you would dissolve the Berlin green and the paper would not make a print. Since we'd rather make a print, we won't do that. Well, not yet anyway.
When exposed to ultraviolet radiation, Berlin green reacts with this energy from the sun and is converted to another chemical called Prussian blue. Prussian blue is also made of iron, carbon, and nitrogen, and its scientific name is iron 2-hexacyanoferrate. No new atoms were added during this reaction. Instead, the ultraviolet radiation rearranged the Berlin green molecules into a new set of molecules. This new molecule is water insoluble and cannot be washed out by rinsing the paper.
So why does it matter if something is soluble or insoluble when making a sunprint? Well, when you put an object on your sunprint paper, the object will block the sun. The rest of the paper will be exposed to ultraviolet radiation, changing its Berlin green molecules into Prussian blue molecules. But the paper covered by the object will not undergo this chemical change.
After about 2 minutes in direct sunlight, you'll put your paper into a dishpan of water. Sounds crazy, right? Don't worry, the paper is made to do this.
Because the exposed paper has insoluble Prussian blue and the paper under your object still has soluble Berlin green, the Berlin green will dissolve into the water, leaving plain white paper behind. The Prussian blue will stay on the paper because it is insoluble. The Prussian blue turns a vibrant blue color, while the area covered by your object becomes a white shadow, showing the image of your object. Super cool.
Fill the dishpan with water. Lay out the towel nearby. You'll dry the prints on it. Have the students' items handy in your acrylic sheets. The acrylic sheets will help to hold down light objects like leaves and flowers.
Start in a shaded area. Place the sunprint on top of a piece of cardboard, blue side up. Place the objects on the sunprint, and if they are thin items, place an acrylic sheet on top of them to hold them in place. Set them out in the sun for 1 to 5 minutes, depending on the sun's brightness. 1 to 2 minutes for very strong light, and 3 to 5 minutes for less direct sunlight. When time is up, bring your print to the dishpan. Drop it quickly into the water. Keep it in the water for about 3 to 5 minutes, moving it around occasionally to better dissolve the Berlin green. So about every time a new sunprint is ready, you can take the previous one out of the water. Lay the sunprint out in the sun on the towel to dry. When dry, you've made a great looking sunprint.
That wraps up week 7. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Erica.
And I'm George. In Learning Labs, we will take the Cornerstone Education Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
outdoor fun. In this activity, students head out to a field or large parking lot to model some, but not all, of our solar system using common household items. The size of our solar system and the amount of space between planets is truly amazing.
Here's what you will need for this experiment: soccer ball, 2 flakes of pepper, 1 grain of salt, 2 straight pins with rounded plastic heads, 4 toothpicks, 2 grapes, one slightly bitter than the other, 2 peas, 9 craft sticks, scotch tape, and a pencil, pen, or fine tip marker.
Each craft stick will serve as a stake/holder for your tiny planets. Use tape to affix the items that represent each planet. Write the planet's name on each craft stick. Number 1, Mercury, a pepper flake. Number 2, Venus, a straight pin. The ball on top is the planet. Number 3, Earth, a straight pin. The ball on top is the planet. Number 4, Moon, a grain of salt. Number 5, Mars, a pepper flake. Number 6, Jupiter, a larger grape. Place on a toothpick or pin and tape to the craft stick. Number 7, Saturn, a slightly smaller grape. Place on the toothpick or pin. Number 8, Uranus, a pea. Place on a toothpick or pin. Number 9, Neptune, a pea. Place on a toothpick or pin.
Pictures and models of the solar system give us an incorrect view of the sizes and distances of the sun and the planets. That's because, to see anything on a picture or screen, the distances between planets and the sun must be shrunk and the planet sizes greatly increased. This means that we think that the planets are way bigger than what they are, and that the planets or our moons are much closer to each other than they are.
To get a better understanding of the sizes and distances within our solar system, students will build part of a proportional solar system using the items from before. Using these items, the class will have the correct sizes and distances between the items based on the sun's size if it was shrunk down to the size of a soccer ball.
Show the students a soccer ball. Tell them that this will represent our sun. Show students a straight pin taped to a craft stick. Tell them that the little ball on top of the pin is the size of Earth compared to the sun. Ask the students to tell you how far they think Earth is from the sun.
Now show them each of the other planets. Line them up next to the sun and tell the students that we are now going to figure out how far each of them are from the sun, the size of a soccer ball.
Put the soccer ball sun on the ground. Pace out the distances for each planet, which is easier than using a measuring tape for this activity. Find the distance for each planet that your outdoor space allows based on the chart provided in the lesson plan. When pacing, have an adult use long steps of about 3 feet each.
If working in a field, students can push the craft stick into the ground and stand next to them. Don't forget to gather them at the end of the activity. If in a parking lot, students can stand in place and hold a stick plus the planet in their hand.
Based on a soccer ball sized sun, you won't be able to pace out all the planets. Try to get at least the 4 inner planets plus our moon. Hopefully, you can also get Jupiter. After that, it is unlikely that you have space or time for much else. For the remaining planets, use visual landmarks, buildings, utility poles, street corners, etc., to estimate their distances from the sun based on the chart provided in the lesson plan. Can you estimate a location for all of the planets from where you are?
If we used a smaller sun, say a baseball, then fitting all the planets into a field or large parking lot would be easier. However, with a baseball-sized sun, most of the planets would be the size of dust.
It's amazing to think just how large space actually is. Compared to the sun, the size of a soccer ball, our planet is just the size of a pinhead, and massive Jupiter is a grape. But what's amazing is that in between them is an entire football field with just a pepper flake from Mars and occasional bits of dust for the asteroid belt. There's nothing else out there. And once we get past Jupiter, the distance to Saturn is another football field with nothing else in it. It's almost 8 football fields from the Sun to the pea-sized Neptune. That's a lot of space.
Even traveling very fast, it takes a long time for objects to move through the solar system. Here are a few NASA spacecrafts and probes that have taken super long journeys to visit distant planets and beyond.
Voyager 1 was launched in September of 1977. It reached Jupiter a year and a half later in March of 1979. It passed by Saturn 3 years after its launch in November of 1980. Using Saturn's gravity, it swung upward away from the solar system. Voyager 1 is the most distant man-made object from Earth and is still transmitting data after more than 41 years in operation.
Voyager 2 was launched in August of 1977. It passed Jupiter in July of 1979, reached Saturn in November of 1980, and kept going through the solar system. It flew by Uranus in January of 1986 and reached Neptune in August of 1989, 12 years after its launch. It kept going, passing by distant solar system objects. Like Voyager 1, it is still transmitting data to Earth.
Just think about that. 2 years to get from Earth, a pinhead, to Jupiter, a grape. Think of how slow you have to move to do that in our proportional solar system. Yet the Voyager spacecraft are moving at over 30,000 miles per hour.
3 other space probes, all launched by NASA, have traveled beyond the planets of our solar system. Pioneer 10 was launched in March of 1972. It passed Jupiter in 1974 and last contacted Earth in 2003. Pioneer 11 was launched in April of 1973. It passed Jupiter in 1974 and Saturn in 1979. It last contacted Earth in 1995. New Horizon is the most recent deep space probe. It was launched in 2003 and reached Pluto in July of 2015. Though it moved through the solar system faster than Voyager 1 and 2, it is now moving slower than they are because the Voyager probes used several planets' gravity to accelerate as they traveled.
That wraps up week 8. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Kira.
And I'm Aaron. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Students to physics. Velocity, acceleration, and force are important physics concepts. In this activity, students will learn about these concepts, calculate rocket velocity, and discover how different masses affect the force and rocket launches. Grab a kid-powered stomp rocket and blast off.
Here's what you'll need for this experiment. Dueling stomp rocket, pen or pencil, a timer, a calculator, 1 or 2 chairs that can be taken outside.
For this activity, students will play with stomp rockets and learn about some basic physics concepts: velocity, gravity, acceleration, and deceleration. They will also calculate their rocket's launch velocity and explore how different masses affect the rocket's height and velocity.
First things first, let the kids have fun taking turns in jumping and stomping on the rockets. Give everyone a couple of turns.
Scientists call how fast something travels in a direction its velocity. When you are driving in your car, you measure the car's velocity in miles per hour. For rockets, we will use meters per second. A meter is a little over 3 feet.
Have a rocket ready to shoot in a vertical direction and be ready with your timer. Each time a student launches a rocket, start the timer. Stop it when the rocket hits the ground. Record your flight times in Table 1 of your lesson plans in the column Flight Time.
Gravity is the force of Earth's mass pulling other objects to itself, like you, me, and the rockets. Gravity causes an object's velocity to decelerate or slow down when it tries to leave Earth, and to accelerate or speed up as it comes closer. As a rocket travels up, it decelerates. When it reaches the top of its flight path, its vertical velocity is 0. It stops moving for a moment. Then it begins to accelerate back to Earth. When it hits the ground, its velocity is the same as when it was launched.
The acceleration of gravity on Earth is 9.8 meters per second squared. This means that for every second the rocket is going up, its velocity slows down by 9.8 meters per second. And for every second that it is falling, its velocity speeds up by 9.8 meters per second.
To discover just how fast a student launched their rocket, take the flight time, multiply it by 9.8 meters per second squared, and divide that by 2 because the rocket traveled the same distance up and down. Record your velocities in the column labeled Velocity in meters per second.
You can also convert these velocities into miles per hour. In the final column, multiply your launch velocities by 2.2. Are you surprised by these numbers?
A force is a push, pull, or other action that accelerates or decelerates an object. When you jump onto the stomp rocket pad to launch the rocket, you are applying force to the rocket.
How strong that force is depends on 2 things: mass and acceleration. We already know that gravity is pulling down at 9.8 meters per second squared. So now we'll see how mass is affecting force.
Set up the 2 chairs by the stomp rockets with 1 launch pad in front of each chair. Students will step off of the chair and land on the launch pad.
Students should not jump from the chairs, just step off. For this experiment, we want to keep the distance down to the launch pad the same for all students. This controls acceleration. This way, only the difference in the 2 students' masses results in different forces applied to the rocket.
Now divide the students into pairs with some big differences in size and some small differences. You can use your timers to measure the flight times for students and record them in Table 2. If you have time, you can calculate the velocities for these launches as well.
As pairs of students step off the chairs and launch their rockets, ask the students, who had the higher or longer launch? Why? How could you get the 2 students to have the same height or time?
That wraps up week 9. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Philip.
And I'm Erica. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
There are 8 planets that orbit the Sun in our solar system. creating a solar system craft, students will make brief presentations about each planet, informing the others on its position, size, atmosphere, and other physical features.
Here's what you'll need for this experiment: a solar system sticker set.
Print out and provide each student with one or more of the planetary information cards included in the lesson plans. Tell them that they're going to be giving a 2-minute presentation on this planet and should work to memorize what they're going to say. For younger students, let them use their cards if they need help.
First, allow the students to construct their solar system craft. After they have completed this, have each student, in turn, bring up their craft to discuss their planet. Begin with Mercury and continue to Neptune, giving 1 to 2 minutes for each presentation. Especially for younger students, instructors or parents can help them along by asking questions that have answers on the cards and lesson plans. Like, does Mars have an atmosphere? Or, how does Uranus spin?
Older students will probably be able to present their cards in less than 2 minutes. So instructors may wish to have them also find out 3 or 4 of their own facts about these planets by visiting NASA's or another reputable website. Ideas for further topics include specific distances from the Sun in absolute or relative values, have any space missions like rockets and probes gone to or studied the planet, when the planet was discovered or first mentioned historically, the Roman god associated with the planet, and talk about them, mentions of particular planets in Scripture.
Did you know that there are actually 13 constellations in the astronomical zodiac? And what is the zodiac anyway? After completing a craft on constellations, students will give a short presentation on their constellation to the class.
Here's what you'll need for this experiment: constellation printouts, pens, pencils, or markers, and optional star stickers or Christmas lights.
Astronomy is the scientific study of space, like stars, planets, comets, and other objects. Astronomy is among the oldest of sciences because knowing where the stars are in the sky was helpful for planting crops, especially in places where seasons are not very different. So it was important to keep track of the sun for the day, the moon for the month, and the stars for the seasons and years.
Constellations are groups of stars that people have decided look like a certain type of thing, like a person, animal, or a mythical creature. There are currently 88 constellations that are recognized in the night sky seen from Earth. The zodiac is a group of 13 constellations that all touch a line in the sky we call the ecliptic. The ecliptic is the path in the sky along which the sun passes. So the zodiac constellations are all in the same line with the sun as Earth orbits around the sun.
During the day, the brightness of the sun keeps us from seeing the stars in the constellations that are behind it. At night, we see the stars and constellations that are in the opposite direction from the sun. As Earth orbits the sun during the year, the stars and constellations that we can see change as the stars are blocked by the sunlight or visible at night. This is why we have different constellations visible in the winter compared to the summer.
Show figures 1 and 2 to your students.
Hand out a constellation sheet to each student according to the constellation they will present. You may pass out extras as well for them to work on for fun. Students will first connect the dots to show the outline of the constellation. Then draw stars or place star stickers over the provided constellation crafts, or poke holes through the star locations and insert Christmas lights.
After completing their craft, have each student, in turn, bring up their craft to discuss their constellation. Especially for younger students, instructors or parents can help them along by asking questions that have answers on the information cards they brought to class for their presentations.
That wraps up week 11 and 12. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with these lessons. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Ethan.
And I'm Kira. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Sound is energy waves that we can hear and even feel. In this pair of experiments, you'll learn about sound frequency and amplitude, and how sound can travel as vibrations through both solids and gases.
Here's what you will need for our first experiment. 3 spoons of different sizes or thicknesses. 1 piece of string for each spoon cut 18 inches long, and a permanent marker. After the experiment is over, you can remove the marker with some household rubbing alcohol on a paper towel. It comes right off. Tie the string at the neck just below the spoon's bowl. That's the real name for the part we put the food in. Double or triple knot.
Students will work in pairs or threes, taking turns with each spoon. One student will take the string and hold it up to their ear with their finger, with the spoon hanging down. Have them plug their other ear with the finger. This will help them hear the vibrations coming from the string without hearing as much of the sound from the air.
The other student will tap the spoon with their finger or a pencil or pen. If working alone, students can swing the spoon onto the side of a table or chair. Students will hear the sound of the spoon coming through the string and up to their ears.
Have the student switch places, with the second student now listening to the spoon as it is tapped. Once each student in the group has had a turn, switch spoons with another group and repeat until all students have experimented with each spoon.
You could hear the spoon when your ears were plugged because the sound traveled from the spoon to your ears through the string. So let's find out how and why that happens.
Sounds are energy waves that we can hear. They are caused by vibrations. To vibrate means to shake or wiggle back and forth. When objects do this with enough power and at a certain speed, we can hear them. When you tap the spoon, you made it vibrate. The spoon's vibrations made the string vibrate, and the string's vibrations were picked up by your ears, so you could hear a sound. Pretty cool, huh?
When you hear a sound, there are 2 things that you notice very quickly: how loud it was and whether it sounded low or high. Scientists use special terms to talk about each of them.
The word amplitude refers to whether a sound is loud or soft. It means volume, so think of it as a TV or radio. Amplitude is a measure of power and describes how tall or short the sound waves are when they are produced by vibrations.
The word frequency refers to whether the sound is low or high. Musicians and singers use the word pitch, and they mean the same thing here. Frequency is a measure of energy and means the number of vibrations that are happening over a certain amount of time. The more vibrations, the higher the frequency of the sound. The fewer vibrations, the lower or deeper the sound is.
Experiment with your own voice with frequency. Squeak out in a high-pitched voice, "Frequency!" Now, say it again at the same volume, but in a low, deep voice. Frequency.
So you can change the frequency of the sound coming out of your mouth. You can also change the amplitude by being louder or quieter.
Here's what you will need for this experiment. A long stem glass. Different glasses will make different noises, so you can use more than one if you wish. 2 plastic cups or bowls, white vinegar, water, and a paper towel.
Put a little vinegar on a paper towel and rub the rim of the glass. As each student comes up, have them dip their finger and thumb in the cup or bowl of vinegar. They will rub their finger and thumb together to remove oils. Then they will dip their finger in the cup or bowl of water.
While gently holding down the base of the glass, the students will rub their finger in a circle around the top of the rim of the glass, lightly pressing as they rub. As they do, the wine glass will begin singing.
So why did that happen? The answer is vibrations. As the students rub the rim of the glass, their finger doesn't move completely smoothly. The small bumps and skips of the finger make the glass vibrate. The steadier the rub, the more regular the vibrations, and the clearer the sound from the glass.
Now, do you remember how the sound from the spoon bells got to your ears? Was the string a solid, liquid, or a gas? How did the vibrations from the glass get to our ears?
This is what we usually experience: sound coming through the air. It is only possible because air is made of molecules that get bumped and vibrate, making the sound wave travel from its source to our ears.
Can a wine glass be broken with just sound? Yes.
When the wine glass made a sound, it did so because it vibrated with a certain frequency or pitch, and amplitude, loudness, or power. A person or electronic speaker can make a sound that is the same frequency as the sound from the wine glass. When they do, they create sound waves that cause air molecules to vibrate. Those air molecules then hit the wine glass, causing it to vibrate also. If the vibrations get strong enough, the glass won't be able to hold together and it will break. But how?
There are 3 parts to breaking the glass with sound. You have to match the frequency of the sound the glass made. If the frequency is too high or too low, the glass will not vibrate properly. The person or electronic speaker needs to be close to the glass, about 1 inch away. This is important because being close concentrates the sound energy onto the glass and makes it vibrate. The sound must be at a higher amplitude. It must be louder than what you made by rubbing the glass. Since just rubbing the glass only made sound, it didn't break the glass, you need more power. The sound needs to be as loud as a strong yell.
Put these 3 parts together and you can break a glass just by using sound. If you go on the internet, you can find videos of people who break a wine glass using just their voice.
That wraps up week 13. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Erica.
And I'm Aaron. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
In the first experiment, students will learn about conduction, one of the 3 types of energy transfer. In the second, they will learn about water surface tension and how it can be disrupted.
Here's what you'll need for the first experiment. Small rug or carpet sample, piece of 8x5 by 11 paper, and aluminum foil.
Have the students take off their shoes and socks and write down the floor material in the upper left of Table 1 from their lesson plans. Divide the students into groups of 2 or 3 and have them rotate through each station. They will place one barefoot on the floor and the other barefoot on the item for comparison, and circle which surface feels colder, or circle both if they feel about the same. Also, if the colder surface feels much colder, then have them put an M by the circle. If it only feels slightly colder, place a S by the circle.
Have the students note the observation in Table 1 from your lessons plans as they go from station to station. Each station, students will circle which surfaces feel colder, the floor, or the item for comparison.
Have the students put on just one sock and have them go to Station 3, the aluminum foil, and stand on it with both feet. What do they observe?
Ask the students, which surface felt the warmest? Which surface felt the coldest of all? Was the floor always the warmest? Did any station have 2 surfaces that felt about the same? Which foot felt colder on the aluminum foil, the bare foot or the one with the sock? Why do you think so?
Your body is working all the time to stay at a certain temperature. The food that we eat is used to keep our bodies warm when the temperatures outside are low, and we sweat to cool off when the temperatures are high. The fact that we are warm-blooded is one of the reasons why this experiment works well.
Heat is actually not an energy itself. Heat is the movement of thermal energy or infrared energy. When we feel something warming us up, thermal energy is being given to us by that something, like a campfire or hot cocoa. When we feel cold, thermal energy is leaving us and going into something else, like chilly night air or a cold glass of milk. Energy only moves from hot things into cold things.
Some materials are really good at moving thermal energy from one place to another. We call these materials conductors. Good conductors are usually made out of metal, like aluminum foil, which you stood on. Aluminum is a very good conductor, and copper is one of the best. They are both often used in making pots and pans for cooking because they move energy so well.
Other materials aren't good at moving thermal energy. They are called insulators. Houses are built with insulation to help keep the warm air in during the winter and cool air in during the summer. Insulation is used to slow the transfer of warmer air to the colder air.
In this experiment, the different materials were touching your feet, and your feet were giving their thermal energy to those materials. Some of them were really good at taking that energy and moving it away from your body. They were good conductors. When they do that, your feet felt cold.
Other materials didn't seem as cold. They were good insulators. Good insulators include cloth, wood, and air. When you think about the carpet or towel used in your experiment, it is made from cloth and it has lots of air. So it is a very good insulator. When you need to hold a hot pan made of a good conductor, like aluminum, you use oven mitts made of cloth and air because they are good insulators.
So when you stood on each of the different items in the floor, your feet felt colder when they were standing on a good conductor, and they felt warmer when you were standing on a good insulator. The aluminum foil felt coldest because it is the best conductor of all the different things on which you stood.
Each of the items the students stood on was the same temperature. They only felt warmer or colder because of conduction. So why did standing on the aluminum foil with your bare foot and a foot with sock feel different? Your bare foot felt colder even though both feet were standing on a good conductor. But your sock made of cloth and air is a good insulator, so it protected your foot from getting as cold as your bare foot. So a good insulator still keeps your foot warm even if it is touching a good conductor on the outside. Here's what you'll need for the second experiment: a bowl, water, black pepper, dish soap, and a toothpick.
Fill the bowl with water and shake pepper flakes onto the surface. The pepper flakes will float. Notice that the pepper flakes move away from each other and become evenly distributed within the bowl.
What is the shape of a flake of pepper? Why does the pepper float? Why do you think the pepper becomes evenly spaced?
Dip the toothpick in the dish soap and then into the water in the middle of the bowl, or just add 1 drop of dish soap. Watch as all the pepper flakes quickly move to the edges of the bowl.
Wow, why did that happen?
The dish soap can break up some of the water's surface tension. When you added it to the bowl, the soap surrounding the groups of water molecules didn't let them stick to other water molecules. Soap does this because part of its molecular structure is attracted to water molecules, or it's hydrophilic, while the other parts don't like the water molecules. They're hydrophobic.
All the pepper went to the edges at the same time because the soap went into the middle of the bowl, and the soap spread evenly in the water from the center to the edges. The water under the pepper was stuck to the pepper and it didn't get soap.
However, if you stir the water gently with a toothpick, you'll see pepper flakes begin to sink. With the water surface tension lowered, the pepper won't float so easily.
That wraps up week 14. Thanks for joining us. Be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Jordan.
And I'm Philip. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
In this experiment, students use glass bottles and water to create their own set of musical instruments and perform a song. Along the way, students will get reinforcement on the topics of vibration and frequency and the reasons why the bottles make different sounds.
Here's what you'll need for this experiment. 7 12-ounce glass bottles, a pitcher of water, spoons or another item to tap the bottles, a permanent marker, and a ruler.
Using the permanent marker, label each bottle A through G. Then place a mark on the bottle with the marker at the following height as measured from the bottom of the bottle: 1 1/4 inch, 5/8 of an inch, 6 1/2 inches, 3 1/2 inches, 2 5/8 inches, 2 3/8 inches, 1 3/4 inch.
With the bottles empty, allow students to tap gently the wide lower part of each bottle with a spoon.
Now fill each bottle with water up to its mark. The bottle should be close to the notes of A through G. Arrange the bottles randomly on a table or desk. Allow the students to tap each bottle with a spoon. As they do, have the students arrange the bottles from the lowest, deepest sound up to the highest sound.
Okay.
Ask the students if the bottles sounded the same. Which bottles have the lowest sound? Is it the bottles with more or less water in them?
We started with an empty bottle. When tapped with a spoon, the bottle vibrated. That is, the glass wiggled back and forth after it was tapped. Those vibrations made the molecules in the air vibrate, and those made more air molecules vibrate, all the way to your ears, and then you heard a sound. The type of sound, like low or high, is made by the frequency of the vibrations. Frequency, also called pitch, is the number of vibrations that happen in a certain amount of time, like each second.
Remember this? We learned about vibrations, amplitude, and frequency 2 weeks ago with the spoon, bell, and singing wine glass experiments.
So the different sounds are made by having different amounts of water in each bottle. The amount of space that the water takes up is called volume. Liquids, like water, will take the shape of whatever container holds them, like a bottle, a glass, or a bucket, but will keep their volume. For example, we can pour the water from one bottle into a bowl, and its volume will be the same. But instead of being in a skinny bottle, the water takes the shape of the wider bowl.
Air also has volume and takes up space inside each bottle. When we add water into an empty bottle, the air is pushed up and out of the bottle because air floats on top of the water. It is less dense than the water. The different amount of water and air in the bottle changes the bottle's frequency when tapped by the spoon. But why?
The answer is that water can absorb some of the energy from the spoon tap, making the bottle have fewer vibrations per time. Fewer vibrations over time mean a lower frequency, which we hear as a lower or deeper sound. The less water, the less energy is absorbed. So the bottles with very little water have higher frequencies and are closest to the sound of the empty bottle.
Now that you've explored why the bottles make different sounds, it's time to play a song. Students learn Twinkle Twinkle Little Star on their tin whistle in the fall. Show the students the top image on page 4 of the lesson plans, pointing out that higher pitch notes with higher frequencies are towards the top of the musical scale, and lower pitch notes with lower frequencies are towards the bottom of the scale. Have the students play Twinkle and This Old Man using the notes on page 4.
And that wraps up week 15. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Kira.
And I'm Keegan. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Students will learn about the diameter of a circular object affecting its acceleration, and how surface area and shape affect how fast an object falls through the air.
Here's what you will need for this experiment: a table or desk, 2 books or 2 pieces of wood that are the same size, a marble or rubber ball, a roll of clear or masking tape, 1 or more cans of corn, soup, or tomato paste, and a can of soda.
Place the books or the blocks of wood under 2 legs of a table or desk. Have the students place all objects on the high end of the desk. Before they release, have them predict which item will roll the fastest. Ask why they chose that item. Count down 3, 2, 1, go, and release the objects. For larger classes, divide the class into 2 groups and do 2 races.
Do this at least 2 times to test for consistency. For larger classes, take the 2 fastest times from each group and have a final 4 roll off to see which item was the fastest of all. So, we've got a bouncy ball, a can of soup, and a can of soda. Which do you think will roll the fastest?
I think it'll be the bouncy ball.
I think it's going to be the soup.
Which items moved down the slope fastest? Were you surprised that the smallest items rolled the fastest and not the biggest or heaviest?
The reason has to do with the item's center of gravity. All objects have a center of gravity, even you. The center of gravity is the spot in an object around which all of its weight is evenly distributed. It's the spot that is the middle of all of your mass. For a circle, can, or ball, the center of gravity is in, well, the center.
But it's not always that way. Your body is certainly not shaped like a wheel. For people, our center of gravity is around our belly, where there's just as much weight of our body above our belly as below it.
Back to the rolling balls and cans. How does the center of gravity relate to how fast something rolls? This is where radius comes in. The radius of a circle is the distance from the middle of the circle to the edge of the circle. Small circles have a small radius, bigger circles have bigger radii.
The smaller the circle is, the closer its mass is to its center of gravity. By having more mass close to the center of gravity, it takes less energy to move the object.
So as you place the books or wood under the table, you created a ramp that the items could roll down. That's where the energy comes from. Gravity pulling the items downward along the ramp, and the energy was equal for all the items.
Since the smaller items need less energy to get going, they started rolling first. Larger items have their mass further from the center, and so were slower at moving.
Here's what you'll need for our next experiment. 1 copy of Circle 1, Circle 2, Circle 3, and Rectangle 1. Scissors, tape, and a ruler.
For students who can multiply with decimals, have them measure the diameter of Circle 2 at the dashed line. The equation for the area of a circle is pi times the radius squared. Then measure the sides of Rectangle 1. The equation for the area of a rectangle is length times width.
Both the circle and the rectangle have an area of 34.5 square inches. Have the students cut out Circle 1, Circle 2, Circle 3, and Rectangle 1.
For Circle 2, cut the dashed line up to the center of Circle 2. Match letter A to B to make a cone shape. Tape the seam with 2 small pieces of tape.
For Rectangle 1, match the letter A to A and B to B to make a cylinder. Tape the seam with 2 small pieces of tape.
Drop Circle 1, the cone from Circle 2, and the cylinder from Rectangle 1. We'll get to Circle 3 shortly.
Which one falls the fastest?
The cylinder fell the fastest, then the cone, then the flat circle.
Why?
The cylinder fell the fastest because it has the smallest surface area. This is the amount of paper that pushes against the air as the shape falls. The push against it from the air is called air resistance. So air resistance goes up or down as surface area goes up or down.
The cylinder only has the thin edge of the paper pushing against the air as it falls. The cone is next because it has a larger surface area than the cylinder, but less than the flat paper. The surface area of the cylinder that the air sees is the same as the size of its open end.
Take the cone and place it wide side down on circle 1. Show the students that the cone's wide end is smaller than circle 1, and so it has less surface area than circle 1, even though they started the same size.
Show students that circle 3 is the same size as the wide end of the cone. This means that they both have the same surface area.
Since they both have the same surface area, which should fall faster? Will the cone, the paper, or both fall at the same speed? Now drop both shapes.
Well, the cone fell faster. Why is that?
Two things are going on here. One is that the cone was a bit heavier, but even if you cut out some of the paper that overlaps to make the weights almost equal, the cone would still fall faster.
Another factor that influences air resistance is shape. Cones are narrow on one end. The narrow end of the cone pushes the air to all sides equally, making a smooth flow of air over the paper as it falls straight down. But circle 3 is flat, so the air kind of bunches up under it, then pushes out to the sides and up. The paper moves back and forth a lot as it falls. This shows that the air is not moving smoothly.
That wraps up week 16. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week. Welcome to Learning Labs with Cornerstone. I'm Izzy.
And I'm Ethan. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Experiments, students will learn about how energy is converted from potential energy to kinetic energy, and how inertia works against forces to resist changes to the motion.
Here's what you will need for this experiment: a marble or a small rubber ball, a 12-inch ruler with a groove in the center, a plastic or styrofoam cup, a pair of scissors, a pencil or a pen, a sheet of paper, and 4 books that are at least 1/2 inch thick.
Use the scissors to cut a rectangle out of the top of the cup, large enough for the marble to enter when flipped upside down.
If doing this experiment by group, print out enough copies of Table 1 and Figure 1 on page 8 of your lesson plans for each group. If experimenting with the demonstration in front of the whole class, then use the table and figure provided, or write it out on a whiteboard and have students fill in the data.
Have students measure the thickness of one book and write it in the heights column. Trial 1, row in Table 1. Next, set up the experiment according to the diagram on page 7 of your lesson plans. Place the edge of the book under the ruler at the 8-inch mark. On the sheet of paper, make a pencil mark where the ruler touches the paper. Label this mark ruler. Place the cup in front of the low end of the ruler and mark with the pencil where the end of the cup is. Label this mark as start. Do this so students can set up the experiment consistently each time.
Now place the marble in the ruler's center groove at the 8-inch mark, just above the edge of the book. Let go of the marble and watch it roll down. When the marble hits the cup is moved backward.
Without lifting the cup, use your pencil and mark where the back of the cup is now. Label this mark Trial 1.
Use the ruler to measure the distance between the Start and Trial 1 marks. Record this distance in the Trial 1 row distance column in Table 1.
Add a second book and measure the height of the 2 books. Record this in the height column, Trial 2 row in Table 1. Place the cup on the paper so the back of the cup is at the start mark. Place the ruler with its lower edge on the ruler mark and the book edge under the 8-inch mark. Put the marble on the 8-inch mark and let it roll down the ruler.
mark the location of the back of the cup with your pencil and label it Trial 2. Measure the distance between the start and Trial 2 marks. Record this distance in the Trial 2 row, distance column in Table 1.
Add a third book and measure the height of the 3 books. Record this in the height column, Trial 3 row in Table 1. Place the cup on the paper so the back of the cup is at the start mark. Place the ruler with its lower edge on the ruler mark and the book edge under the 8-inch mark. Put the marble on the 8-inch mark and let it roll down the ruler. Mark the location of the back of the cup with your pencil and label it Trial 3. Measure the distance between the start and Trial 3 marks. Record this distance in the Trial 3 row, distance column in Table 1.
Now that students have 3 trials of data, have them plot their data as a graph in Figure 1.
Then have students use their ruler to draw one straight line that starts at the lower left corner of the graph and comes closest to all of the data dots. They should not connect the dots. Instead, draw just one line that seems the best for showing the trend in the data. Have that line go out past their 3rd trial data dot.
Have students measure the height of all 4 books and record the measurement in Table 1. Find that height on the left side of the graph and draw a light pencil line straight across to the line they drew before. Put a small circle where these 2 lines connect. Then draw a light line straight down from the circle to the distance at the bottom of the graph.
Based on this data, a prediction for the distance a cup would move when hit by a marble starting 2 inches high would be almost 2.5 inches. Now, test the prediction.
Set up the experiment as before and release the marble. Mark the place where the back of the cup ended and label it Trial 4. Measure its distance from the start mark and record that in Table 1. Then plot it on your graph. How close was your prediction?
This experiment shows us how an object, the marble, converts one form of energy into another and then transfers that energy to another object, the cup.
When the marble is first placed on the ruler, it has potential energy. This is energy that is based on the object's height. The more books that were stacked, the higher the marble was placed, and the more potential energy it was given.
When you released the marble, it began to roll down the ruler. This is because gravity pulled the marble down. Gravity is a force that attracts 2 objects. In this case, the objects are the earth and the marble. As the marble rolled down the ruler, its potential energy decreased because it went lower than where it started.
However, the marble was moving, and now it had kinetic energy. Kinetic energy is the energy of motion, and the faster the marble went, its kinetic energy increased. So, as the marble's potential energy decreased by falling, its kinetic energy increased by moving faster. The marble's potential energy was converted to kinetic energy.
As the marble rolled down the ruler, it accelerated because of gravity pulling it down. First, it started rolling slowly, but by the middle of the ruler, it was faster, and when it came off the ruler, it was even faster. Acceleration is an increase in an object's velocity. When the marble came off the ruler, it went onto the flat table and was moving as fast as it could. All of the potential energy was now turned into kinetic energy.
Then the marble hit the back of the cup, and it pushed the cup backwards because of its kinetic energy. The cup has mass too, but wasn't moving. But when the marble made the cup move, its energy was transferred to the cup and made it move.
Our measurements showed us that by placing the marble higher, it will move the cup further than when it hits it.
That wraps up week 17. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs or Cornerstone. I'm George.
And I'm Erica. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
In this pair of experiments, students will learn about how screws work, their history, and their many uses. Then they'll discover how an inclined plane relates to a screw.
Here's what you'll need for this experiment. 3 or 4 different types of screws, 3 sheets of printer paper, and a pencil for each student.
Give 1 copy of parts of a screw to each pair of students, and hand everyone a sheet of printer paper and pencil. Given each group several different types of screws, have students take some time to draw each screw on their paper and identify each part as seen in the illustration in your lesson plans.
Some parts, such as the shank, may not be present on all screws. Have the students compare their screws in these ways. Are all the screws the same length or width? What are the different shapes of screw heads? Is the pitch or downward angle of the thread the same for all the screws? Do all the screws have pointy ends, flat ends, or some of each? How do you think these screws might be used? Could they be used for wood, metal, or plastic?
Nobody knows who invented the first screw. The screws are mentioned in the writings of ancient Greeks around 300 to 400 BC, and by the time of Jesus' birth, screws were being used throughout the Roman Empire. These early screws were made of wood, not metal like the ones we have today, and most of the ones we know about were used for grape and olive presses. During the Middle Ages, this type of screw press was also used for making printed paper.
The first metal screws were invented in the 1500s, but they were very difficult and time-consuming to make, so they were rare. At this time, both wooden and metal screws were often used to put thin pieces of wood or metal together. Screws are good at holding things together, but these early screws did not have any holes or grooves on their top, so you couldn't unscrew them. If you needed to separate the pieces, you had to cut the screw.
In the 1700s, machines were built that could easily make metal screws. Those screws only had flat ends, not pointy ones. Screws with pointy ends were invented later on in the 1800s. So the screws you're using in this experiment are a pretty recent invention that is part of a very long history. Also around this time, people began to realize that screws could be used for lots of different things, from fastening 2 things together, moving boats with propellers, and lifting and supporting buildings. It turns out that the screw is a really useful invention.
Working in pairs, have the students take one of the screws and stand it up on their desk or table with the head of the screw on the desk. Then take a piece of paper and gently poke the screw through the paper just enough to get it into the thread.
Have one student hold the edges of the paper while the other student turns the screws counterclockwise with their finger and thumb. As they do, the screw will draw the paper down. Turning clockwise will move the paper up. Let students change places and repeat.
Notice that the paper stays in between the threads. Have the students try this with their other screws. As they do, ask them, do all the screws move up and down the paper the same? What is the relationship between the pitch of the screw and the amount of turning you need to move the paper?
Here's what you will need for our second experiment: 2 pencils, scissors, tape, and a printout of the triangles from page 7 of your lesson plans.
Pass out all the items to the students. Have the students cut out the 2 triangles from page 7 of the lesson plans. Have them compare the shapes to each other. They are both the same height, but one is wider than the other. The wider one has a less steep angle going from bottom to the top than the other.
Have the students tape the vertical edge, side A and B, of the triangles to their pencils. Then wrap the triangle around the pencil completely so that you can see the dashed line as it wraps around the pencil. Place the tape at the bottom so it will not unroll. Observe the pencils. Which one has more visible dashes?
The triangles are an example of an inclined plane. A plane is a flat surface. To be an incline means to be raised on one end. If you think about it, you've seen lots of inclined planes. They are seen on ramps for wheelchairs and as wooden triangles that hold doors open. Inclined planes make it easier for us to go up and down hills, to lift things up, or to stop things from moving. They are very useful tools.
When we wrap the triangles around the pencil, we turn the inclined plane into something that looks like a screw. The dashed lines help us see the inclined plane as it goes around and around the pencil.
When we do this, the dashed lines are just like the thread of the screw we looked at before. The steepness of the triangle is just like the pitch of the screw threads. A steep inclined plane, when wrapped around a cylinder, makes a screw with a big pitch with few threads per distance on the screw. A long, low inclined plane will make the screw with a smaller pitch with more threads per distance on the screw.
Ask the students, if you were trying to lift something very heavy using screws, would you want a steep pitch or a shallow pitch? If you wanted to move something with a screw using the fewest number of turns, would you want a steep pitch or a shallow pitch?
That wraps up week 18. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Gracie.
And I'm Aaron. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Using paper airplanes, students will learn about the 4 forces most important to flight: lift, thrust, drag, and gravity. Different paper airplane designs address these forces in different ways, making airplanes that are fast or slow, fly long or short distances, and fly straight or in circles.
Here's what you'll need for this experiment. Printouts of paper airplane design instructions for your students. 2 or 3 sheets of paper per student. Scissors, markers or colored pencils to decorate the airplanes.
Pass out the airplane designs and paper to students. Have them make 2 or 3 paper airplanes and decorate them with markers. Test the designs by flying them all around the room.
It is amazing to watch birds fly. Small birds like sparrows and chickadees dart through the air. Hawks and vultures slowly circle higher and higher. For most of human history, all people could do was look at birds and wish that we could fly too. Ask your students, how many of you would like to be able to fly?
Well, on December 7th, 1903, the first successful airplane was built and flown by 2 brothers, Orville and Wilbur Wright. Ever since then, people have been making and improving airplanes to do a lot of different jobs, from carrying people and packages, to fighting in wars, to fighting fires.
Even though so many different airplanes do so many different type of jobs, they all have to balance 4 forces in order to take off, fly, and land safely. Your paper airplanes are affected by each of these forces as well, so let's look at them.
The 4 forces acting on a plane are grouped into 2 pairs based on their effects.
Thrust and drag affect the forward motion of an airplane. Thrust is the force that is moving the airplane forward. Drag is the force of the friction of the air which slows down the plane. The amount of thrust depends on the power of the engines, and the amount of drag depends on the surface area of the plane, or how much of the plane you can see when looking straight at it.
Remember how a small surface area helped the cylinder and cone fall faster than the flat paper a few weeks ago? The smaller the surface area, the less drag the airplane will experience. This means that the airplane needs less energy from thrust to move it forward. Reducing drag makes airplanes more efficient.
The other pair of forces are weight, pulling down, and lift, pushing up. We can stand on a scale and it tells us how much we weigh in pounds. Our weight is a measure of our mass, or how much matter we have in us, and the force of gravity acting on us. Things that weigh a lot are harder to pick up. Airplane designers try to reduce weight so they can also reduce the amount of thrust needed from energy sources like fuel. The energy from fuel in the engines produce thrust. Thrust and lift work together to make an airplane fly, while drag works to slow the airplane and weight tries to pull it back to the ground.
Lift is the force that pushes an airplane up into the air. To make a lift, airplane wings have a certain shape.
Notice that the top side of an airplane wing is curved, while the bottom is straight. If you stretch the top side straight, it would be longer than the bottom side. This is important because as the wings go through the air that gets split at the front of the wings has to meet at the back end of the wing.
To do that, the air that goes over the top of the wing must move faster than the air going under the wing, because it has to go a longer distance than the air under the wing.
This faster moving air creates an area of low pressure above the wing. Low pressure pulls things towards themselves. A vacuum cleaner works by creating an area of low pressure that pulls air and dirt up and inside.
The slower moving air under the wing creates an area of high pressure, which pushes things away. So the low pressure above the wing pulls the wing up, and the high pressure pushes the wing up. This is how an airplane wing creates lift.
The largest airplane ever built was the Antonov An-225 Mriya. You will not be surprised to know that it also had the largest wingspan of any aircraft placed in service, since to fly the heaviest weight, you need the most lift, plus lots and lots of thrust. The Mriya has transported a load weighing 559,580 pounds.
Whether it is the largest aircraft ever built or tiny drones whizzing around the park, all aircraft are affected by the same four forces: thrust, drag, weight, and lift.
Your paper airplanes have all these forces working on them too. Thrust comes from your muscles when you throw the airplane. Drag comes from the surface area of the paper that goes against the air. Your paper airplane has the weight of one piece of paper. The fold of the front of your airplane's wing creates lift. More lift can be made by making upward angle flaps along the back of the tail.
That wraps up week 19. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs of Cornerstone. I'm George.
And I'm Julia. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Have fun storming the castle. During the medieval period, the use of siege towers reached its peak. In this activity, you work on building a tower out of drinking straws to reach over the top of the enemy's walls and bring victory to your army.
Here's what you will need for this experiment: 100 straight plastic straws, tape, scissors, paper, pencils, string, or twine.
For thousands of years, people build walled cities to protect themselves from invading armies. And for thousands of years, invading armies have worked to overcome walls and other fortifications to conquer cities and take over lands. To do this, invading armies often laid siege to a city. During a siege, the attacking army surrounds the city, cutting off the city's access to food and other supplies to force the city's inhabitants to surrender. But most cities didn't give up just because they were surrounded. With stores of food, water, and weapons, the cities would fight back from the safety of their walls, hoping that their defenses and resistance would force the attacking army to abandon the siege.
But how do you attack a walled and defended city? With siege engines. Today, when we hear the word engine, we often think of the machines that power cars, trucks, and boats. But in the ancient and medieval world, an engine was simply a device or structure used to do a job, and they could be small or huge. So a siege engine was some kind of device used in siege warfare. Common siege engines included projectile engines like catapults, mangonels, ballistas, and trebuchets, gate-breaching engines like battering rams, wall-breaching engines like siege towers.
The siege tower was an especially important type of siege engine. Its goal was simple: get a group of soldiers on the top of the wall so they can overtake the city. So as their name suggests, siege towers were tall. How tall? They were often made by the army at the site of a siege and built taller than the city walls so that the archers could fire arrows over the wall from the top of the siege tower. Most siege towers were between 30 and 50 feet tall, but the largest siege tower known, the Heliopolis, used at the siege of Rhodes in 305 BC, was 130 feet tall, 65 feet wide at the base, and needed over 3,400 men to move it. It was so large that it contained 16 catapults.
Siege towers had wheels at their base so they could be built at a safe distance and then moved to the best location against the city. The front and sides of the siege tower would be covered in water or vinegar-soaked animal skins or metal plating to prevent them from being set on fire by the city's defenders. The top of the tower had a gangplank or drawbridge, which would be lowered to connect the siege tower to the city wall and allow the invading troops to cross onto the wall. Some siege towers also were built with a battering ram or large drill at their base to break down the walls or gates.
The first records of siege towers come from the mid-800s BC in Assyria. They were used by many armies over time in both the West and the Far East. The use of siege towers reached its greatest extent in Europe during the medieval period, since the fall of the Roman Empire resulted in Europe fragmenting into scores of warring city-states and the building of castles became widespread. The growing use of gunpowder and cannons effectively ended the use of siege engines during the 1400s. Since invading armies could attack from longer distances on the ground and defending cities could destroy approaching siege towers with their artillery.
Younger students, pre-K through 4th grade, work in pairs to build a simple tower for this activity using drinking straws, tape, and scissors. Top marks go to the team that makes the tallest tower in the time allotted.
Students in 5th and 6th grade can add to the challenge by building a tower with one of the following requirements. The tower is at least 3.5 feet tall. The tower has 3 or 4 levels. The tower has a gangplank or drawbridge near its top that can be raised and lowered with a string. The tower has a battering ram in its lower section that consists of a bundle of straws suspended by a string so that it can be pulled back and swung forward. We found while building our towers, 2 things were crucial. Triangles are your friend. Have students try building triangular structures to add support to their towers as they build taller. And, of course, teamwork is a must. Most likely, students will not be able to complete their dream tower in 30 minutes. However, with great teamwork, they will create some pretty awesome and unique structures.
That wraps up week 21. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week!
Welcome to Learning Labs with Cornerstone. I'm Erica.
And I'm Ethan. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Involves the history and forces used in catapults and making 2 different catapults that can throw mini pom-poms.
Here's what you'll need for our first experiment: 16 craft sticks, 2 wooden spoons, and mini pom-poms.
Last week, we learned that siege engines were devices and weapons built for use during the siege of a fortified city or castle. One of the most important types of weapons in siege warfare was the catapult, a device used to throw objects at or over the fortified wall of a city or castle.
The earliest use of catapults may come from the Bible. In 2 Chronicles 26:15, Scripture mentions that King Uzziah of Judah ordered his men to build engines and place them in towers to shoot arrows and great stones. This would have been in the middle 700s BC. Catapults were used widely in the ancient world of Greeks and Romans, as well as in the Far East. Their use continued through the medieval period until the invention of gunpowder and cannons made them obsolete.
Catapults are a group of weapons and not just a single type. Designs for catapults depended on what type of energy would be used to move the swing arm. 3 basic categories for catapults include the trebuchet, a gravity-powered catapult, the mangonel, the kind we think of most when picturing a catapult. It has a long swing arm with a bowl-shaped bucket, and the ballista, a very large crossbow.
While trebuchets usually used gravity, mangonels and ballistas used either tension or torsion to provide energy for launching their payload. Tension occurs when an object, like a rope or wooden beam, is pulled back and flexed. It wants to snap back into its original position. Your catapults today will use tension for their energy source.
Torsion occurs when an object is twisted, storing energy that is released when the object is allowed to rotate back into position, while tension provides a good power and is limited by the ability of a single object to snap back into position. Torsion provides more power than tension, but the gravity-powered system of the trebuchet is the most powerful of all.
Have the students stack 5 craft sticks together and wrap a rubber band around tightly at one end of the stack. On the opposite end, insert a craft stick between the bottom craft stick and the rest of the stack. Make the inserted craft stick perpendicular to the others and slide it to the middle of the stack. It should look like a cross. Wrap the other end of the stack of craft sticks with a rubber band. Place the spoon on top of the stack facing up, lined up with the perpendicular craft stick. Wrap a rubber band around the end of the spoon and the perpendicular craft stick. Place a pom-pom in the spoon and shoot.
Make a square with 4 craft sticks and wrap a rubber band around each corner to hold it together. Put this square to the side. Make 2 triangles of 3 craft sticks each, wrapped at each corner with rubber bands. Attach one of the triangles to the square using the rubber bands at 2 corners. Repeat this on the other side with the second triangle. The tension from the rubber bands will likely make the triangles lay down over the square. Have one student hold the 2 triangles upright. Another student will place a craft stick across them and wrap each end with a rubber band. This is the upper cross stick and is the front of the catapult. Take another craft stick and wrap a rubber band around 4 or 5 times, about 1 inch from the left edge. Place this craft stick across the same side as the upper cross stick, but lower down at about the halfway point. Loop the remaining length of the rubber band around the back of the front stick of the triangle and back onto the left edge of the craft stick. This is the lower cross stick. Do this on both sides. Thread the spoon handle down through the cross sticks so that the lower part of the handle is in front of the lower cross stick and the upper handle is behind the upper cross stick. Place a rubber band across the back side of your square base. Pull the front portion under the base and all the way to the lower end of the spoon handle. Place another rubber band around the top of your 2 triangles with one side of the rubber band in front of the spoon and one side behind it. Place a pom-pom onto the spoon, pull back, and shoot.
That wraps up week 22. Thanks for joining us, and be sure to keep your Cornerstone lesson plans handy to help you with this week's lesson. See you next week.
Welcome to Learning Labs with Cornerstone. I'm Phil.
And I'm Kira. In Learning Labs, we will take the Cornerstone Educational Supply lesson plans a step further and provide tips and tricks for what to look for when performing your experiment.
Rubber bands, and tissue paper, pairs of students will build and test a protective device that will keep an egg from breaking when dropped from a given height.
Here's what you will need for this experiment. Each group of students will need 50 craft sticks, 50 rubber bands, a box of tissues or a roll of paper towels, 1 plastic egg for building time, and each class will need uncooked eggs, a plastic garbage bag if dropping the egg protectors inside, and a kitchen scale if weighing the egg protectors.
Pass out the craft sticks, rubber bands, tissues, and plastic eggs to each group. For younger students, their challenge is to build an egg protector that can keep an egg from breaking when dropped from 10 to 15 feet. Use the plastic egg during design and a real egg during the test. Drop eggs from above your head while standing on top of a desk, out of a second-story window or balcony, or from a ladder. Lay out the garbage bag on the floor if dropping the egg protector devices indoors.
To make the activity more challenging, introduce a low weight preference for the egg protector, much like the low-cost straw bridge construction in week 20.
Each team represents an engineering firm, and they are tasked by NASA to create a space reentry module to be used when bringing astronauts back from the International Space Station. NASA is interested in your egg protector design as a prototype, but only if it survives the rigors of NASA's crash test lab, that is.
Surviving reentry is obviously the most important factor for your device, but bringing the reentry module up to the ISS uses a lot of fuel, so NASA wants the device to be as light as possible. The winning design must be able to protect the egg from breaking when dropped from 25 to 30 feet and be the lightest design in the class. Use the plastic egg during design and a real egg during the test.
The device's mass can be measured directly with a kitchen scale or use the values provided here. 1 craft stick is 1.4 grams. A rubber band is 0.2 grams, and 1 facial tissue is 1 gram.
Students will keep track of the number of items used in construction and produce a final mass to their NASA liaison, the instructor. At test time, drop the devices out of a second or third story window, down the middle of a long stairwell, or from a high balcony. You can even throw them up in the air and let them free fall. Lay the garbage bag out on the floor if dropping the egg protector devices indoors. The team whose device is the lightest while keeping the egg intact wins. I went for a simple design. My hope is that the popsicle sticks will bounce off the ground and keep the egg intact.
I went for a more complex design. I went with the triangles, but also with a lot of padding. All right, Kira, ready?
Yeah, I'll go first. 3, 2, 1. Oh no. Well, my egg was definitely not protected. Philip, do you want to try yours?
Well, sure. I feel pretty good about mine. 3, 2, 1. Well, we just dropped our eggs, and Kira?
Mine is completely destroyed. What about yours, Philip?
Mine stayed intact. Success. Eggs are tough, but they can't survive a trip to the floor all by themselves. This kind of activity prods us to think about forces, direction, and the materials we use when building devices and contraptions.
The egg will be pulled toward the ground by the force of gravity. The higher the starting point, the faster the egg will move toward the ground because gravity causes an object, the egg, to increase its velocity, speed, over time until it makes contact with the ground. Without some help, your egg will go splat.
For your egg to survive, you have to slow it down somehow. And there are a few ways to do this. Number 1, build a parachute. This works well if you have the right materials, but craft sticks, rubber bands, and tissues just might not work as well as you hope. This brings us to our other options. Number 2, padding. Lots and lots of padding. Stuffed well, but still loose enough so the egg doesn't crunch or bounce. Think of it like an airbag for your egg. The longer it takes for your egg to move through the padding, the longer the force of impact is spread over time. Slowing down your egg keeps it safe. Make a web of rubber bands and use plenty of tissues. Just don't let the egg fly out of your contraption. Have some webbing over the top of the egg also to make sure you don't bounce it out of the protector. If that happens, your egg could be scrambled. Number 3, crumple zones. Slow down your egg by creating an egg protector that is designed to break on impact. By letting parts of the egg protector crumble, bend, and break, The force of impact will be absorbed, slowing down the egg before it hits the ground. Use long spokes from several craft sticks in a row and make the rubber band connections between them loose enough that the sticks can bend and slide. Take care in your design that none of your craft sticks point towards the egg. Otherwise, you could end up with a gooey egg sickle. Gross.
Some designs, like a cylinder, have a heavy end at one side so that the device will land on the heavy end. If using this style, keep the egg a bit above the middle of the cylinder with lots of cushioning under the egg with tissues and a web of rubber bands, both above and below the egg. This reduces the force of the egg experiences as it travels through the padding. The lower forces mean safe eggs.
Other devices are the same shape all around and might hit the ground on any side or at any angle. Remember how helpful triangles were in making a successful bridge in week 20? Well, triangles are also helpful in building an egg drop device because they can distribute the force of impact with the ground around your egg. Start by making a triangle of craft sticks tied at the ends with rubber bands. Make 3 of these triangles, put the egg in the center, and tie them together. Make sure none of the triangles have sticks pointing at or into the egg. Once this is built, teams can add long sets of craft sticks loosely tied with rubber bands to act as crumple zones.
Similar to this design, you can also try cubes. Keep your egg in the center of these structures with both the frame and some rubber bands. Use more craft sticks to make long collapsible extensions held loosely with rubber bands so that they will slide, bend, and break on impact however your device hits the ground.
And that wraps up week 23. Thanks for joining us for Cycle 2. See you next year.